Hello. Today I want to talk about the idea of an inverse relation and also an inverse function. You may have seen inverse functions in a pre-calculus course, maybe in a college algebra course. Here we're going to do it in a little more formality and a little more generalized setting, looking at it almost as a special case of an inverse relation, right? So what is, once again, let's remind ourselves, what is a relation, right? A relation is just ordered pairs from a subset of a Cartesian product, right? A cross B is a set of all ordered pairs with one coordinate chosen from set A and one coordinate chosen from set B. So R is a subset of these ordered pairs, is a relation. Well, what is an inverse relation? It's also a relation, but it goes the other way. It's from set B to set A, right? So it's a subset of the cross product B cross A instead of A cross B. You reverse the domain and codomain, right? So that's what we're noticing right here. Notice that right, we interchange the domain and codomain, right? Those got flipped. And how do we define it? Well, we just say B is related to A, that is the pair B comma A is in the relation R inverse whenever the pair AB is in R. Or another way to say it is R inverse relates B to A whenever R relates A to B. That's another way to say it. So here's an example of an inverse relation. So you could say, for example, the relation less than on the set of real numbers, right? This is a perfectly good relation, has inverse relation greater than, right? So this is, if R is the relation less than, then R inverse is the relation greater than, because I want to say that R contains what? What kind of pairs are in R? Well, any pair where the first number is less than the second number. And so on. And here there are uncountably many, so we can't really list them out, but just to show some examples, right? These are all ordered pairs where the first is less than the second. So what would the inverse relation look like? It looks like all examples, all ordered pairs where the first is greater than the second. Right, 1.1 is greater than 1 because 1 was less than 1.1, right? Pi is greater than 2 because 2 was less than pi, and so on, right? So if we just reverse all these ordered pairs, we get the inverse relation, right? Another way to look at this, of course, is with our blob diagrams, right? So you can think of 1 over here and 1.1 over here. So the relation R, which is the relation less than, would relate 1 to 1.1, right? But then the relation R inverse, which is the relation greater than, would relate 1.1 back to 1. Right, so this is the idea of an inverse relation, right? Now, this example, these relations are not functions, right? So here I have a relation and I define the perfectly good inverse relation, right? But note that this R is not a function, right? Why is it not a function? Well, because say 1 is related to 1.1, but 1 is also related to pi, right? So you have the same input going to two different outputs, right? So it's not a function. It's a perfectly good relation, but it's not a function. Now, the case that I'd say we're most often interested in with regards to these inverse relations is the case where the relation does happen to be a function. So let's think about right, if R is a function, and let's now switch to function notation, right? We'll switch to f. If your relation happens to be a function, right, and we'll call it f. So once again, remember our notation for it. We say A is related to B if and only if we write B equals f of A, right? This is our notation. Then we can define F inverse in exactly the same way. Right? You just reverse all the ordered pairs from R, right? So, right, we reverse all ordered pairs in the relation R. So if you want, for example, to think about the function, and let's say this function goes from the reals to the reals, and let's say it's given by f of x equals x squared. Right? What does this look like? This function looks like what? Well, 0 goes to 0, right? 1 goes to 1, but so does -1 go to 1, right? 2 goes to 4, but so does -2 also go to 4, and so on, right? So this is a copy of the real numbers. This is a copy of the real numbers. And here I'm just putting pairs. They're putting arrows that show related objects by this function, right? This special type of relation, which happens to be a function. So if you're writing this out as ordered pairs, right? What are the ordered pairs that correspond to this? The ordered pairs in this relation would be, so in the relation F would be 0, 0, right? 1, 1, -1, 1, 2, 4, -2, 4, and so on, right? And again, I can't exhaustively list these because there are zillions more in between, right? There's √2, comma 2 is in there, and right, we're working on the real numbers, so there isn't a good scheme for listing these, but I'm just showing some examples of ordered pairs in F. And note that these ordered pairs that we're writing, when we write the ordered pairs for a function, that come from this idea of thinking of the relation as a subset of the cross product, right, of the Cartesian product. These are exactly the ordered pairs that you graph when you graph a function, right? You're showing that this number got related to that number, and then you plot that point, right? So this is, so we're sort of listing out ordered pairs, and now here we're doing, when we graph, we're doing exactly the same thing. We're just showing these ordered pairs, plotting them as horizontal comma vertical, as opposed to listing them out or drawing this arrow diagram. But I just want to mention that this is sort of new notation for something very familiar, the graph of y equals x, right? Y equals x squared, and the points on the graph of y equals x squared. So this is what we have so far. Now let's think about the inverse relation for this. What would the inverse relation? The inverse relation is, which we'll call F inverse, right? This would have all the same ordered pairs, but in the opposite order, right? So it'd have ordered pairs like 0, 0. That one stays the same, right? When I reverse the coordinates on 0, 0, you can't tell I did it, right? And 1, 1 would also stay the same. But then -1, 1 would actually switch to 1, -1, right? And 2, 4 would switch to 4, 2. And 4, -2, 4 would switch to 4, -2, and so on, right? So you can kind of see what this relation is. Really what we're getting here, if you want to describe F inverse, how is this relating elements? It says A by F inverse is related to B if and only if what? Well, here B would have to equal the square root of A, or B could equal minus the square root of A, right? Every first coordinate is getting related to two separate second coordinates, right? 4, for example, got related to both 2 and -2, right? So this is our description of this relation F inverse, right? So this is if we want to describe this relation directly, this is how we would have to describe these ordered pairs, right? So first I just sort of listed ordered pairs from up above, right? But now I'm getting a general description of these new ordered pairs, right? Okay, so what can we do next? Well, we can ask, is this a function? Right? This relation, right? Is this relation F inverse? Is it a function, right? It's a perfectly good relation. Right? Anytime you take the inverse of a relation, you get another relation. Similarly, anytime a function is a special type of relation. So if you take the inverse of a function, the inverse relation of a function, you certainly get a valid relation. But is this new relation that we've created a function or not? Well, in this case, no. Because why? Because here we are pairing each input with two outputs. Right? Each input is getting paired with two outputs. And remember the definition of a function. Each input has to get paired with just a unique output, right? Each first coordinate gets related to only a single second coordinate. So this is an issue, right? This is a big issue in terms of being a function, right? This does not count as a valid function. So here is then what this looks like graphically, right? Suppose I take all these points, 0, 0, 1, 1, 1 minus 1, 4, 2, 4 minus 2. Take all these points and graph them, right? What if you graph all of those, what does it look like? Well, it looks like this, 0, 0, 1, 1, 1 minus 1, 4, 2, 4 minus 2. Right, so this would be the relation. This is the graph of the relation F inverse, right? And now this fails to be a function, right? Because we have inputs being paired with multiple outputs. Which directly violates the definition of a function, right? So this often is referred to as the vertical line test, right? So you may have heard this, right? It fails the vertical line test. That you can find a vertical line that that intersects the graph in more than one location, right? So it fails the vertical line test. So that's an issue here. Right? So there's also another issue though, which is to say that F what were the domain and codomain? Well, they were the real numbers and the real numbers, right? But there's another issue. When you turn around this to F inverse, the domain and codomain still are both real numbers, right? So you have this issue of this F inverse is undefined on a lot of its domain, right? So you kind of have two problems. Over here, the vertical line is intersecting the graph 0 times, right? So over here, it's undefined. And over here, the vertical lines are intersecting the graph 2 times. So we're really not succeeding at having our function, our supposed function F inverse, assign exactly one output to every input in the domain, right? Because in some places it's assigning 0 in outputs to a given input, and in some places it's assigning 2 outputs to a given input. So now how can we fix this? Well, there are two things, and when I say fix, what do I mean? I mean to make an inverse function, to have, not just have an inverse relation, but to have an inverse function, right? How can we make an inverse relation, right, into an inverse function, right? We would love to have, whenever possible, our inverse relations actually be inverse functions, because we work with functions all the time in mathematics, right? It's extremely helpful if we have functions and not just relations. So there are kind of two things that we need to do in order to fix it. So here's our theorem that I actually mentioned in a previous video, right? Is that a function f is invertible. And what do I mean by invertible? I mean that the inverse relation, F inverse, is a function. It is itself a function, and not just the relation. Right, so a function is invertible if and only if it is a bijection. Right, that is, we need f to be both one-to-one and onto. Right, one-to-one, also known as injective, and onto, also known as surjective. So we have a way to accomplish both of these, right? So how can you accomplish this? Well, how can you force f to be one-to-one? The trick is you want to restrict the domain, right? So look at this function. F goes from the reals to the reals. Right now, it's not one-to-one, right? This is not one-to-one. It fails the horizontal line test, right? Which is just like here, we said our F inverse failed the vertical line test. Well, that's equivalent to the original F failing the horizontal line test, right? And then we had a horizontal line intersecting it twice. So what do you do? Well, restrict the domain. Throw away half of the graph, right? And it actually kind of doesn't matter. You could keep just the right half or just the left half. Or you can even keep just the proper subset of the right half or of the left half, but you have to throw away half, right? At least half. So unless we restrict the domain. So I am going, in this case, to say, let's keep just 0 to infinity as the new restricted domain. So keep this part of the graph. This is the new domain. And once I do that, now I actually have a one-to-one function, right? This function, this is now one-to-one, right? So once you restrict the domain, now you do have a one-to-one function. And notice, see now F as a relation has ordered pairs like 1, 1, but not ordered pairs like -1, 1, right? -1, 1 has been excluded from this relation because we threw away that ordered pair when we shrunk the domain, when we shrunk the first set. The set capital A is smaller now, right? It now only contains 0 to infinity and not all real numbers. Right? So this is how you can make a function be that isn't one-to-one be one-to-one by restricting the domain. Right? Now, very similar follow-up question. How can we make F be onto or surjective? Right? Well, there you want to restrict the codomain. Because we had lots of outputs that weren't getting used, right? When you take x squared, you miss all the negative numbers, right? So, for example, this function. So let's keep this domain restriction that we picked, right? This is not onto, right? It's not surjective, and I'm doing the same formula here. F of x equals x squared. Same example. This is not onto because, for example, I'm going to pick the y coordinate -1, right? Never gets used, right? There is no x coordinate, right? There does not exist an x in this domain such that f of x equals -1. It doesn't happen, right? So in that codomain, I have this value, -1, but it never gets used, right? So let's restrict the codomain to just equal the range, right? So restrict the codomain R to instead be, so here's our graph. Well, the range, that's just the set of all y values that actually gets used. This is actually the same interval as what we just picked for our domain restriction, right? It's again just 0 to infinity. Those are the y coordinates that get used. So here's now a new function. So the function, this function, f from 0 to infinity, also mapping to 0 to infinity, right? This function is now onto, because it uses every single y coordinate, right? Is now onto. So you just replace the codomain with the range, right? Restrict the codomain down to the range, and now you have a onto function, an onto version of that same function. So this function now is onto, right? So, and it's one-to-one, right? We threw away the left half of the function, so it's also one-to-one. So this is now bijection, right? This function from 0 to infinity, mapping onto 0 to infinity, is now a bijection, right? And sorry, this is a bijection, and people are excited. They want to celebrate with us. So, and this is our formula, right? Is f of x equals x squared. So we have our bijection, and now F inverse, which maps 0 to infinity to 0 to infinity, is also a function. Right? It's not just an inverse relation anymore. Now it's a function. It's not a function. And I can even say what the formula is. It would be F inverse of x equals the square root of x. It's not equal to root x or negative root x like it used to be, right? So now I have, see, this function f with a restricted domain and codomain is now this graph, which corresponds to this inverse, which looks like this, right, is our F inverse, right, an ordinary square root graph, right? So there's very familiar objects, right, but perhaps new language and new, a little new ways of looking at it, right, where we're very carefully saying what domain and codomain is at every step of these relations and these functions that we're talking about. So, all right, so there's just a quick recap. What did we say today? We said that any relation, given any relation, you can always define an inverse relation by simply reversing all ordered pairs, right? If A is related to B, then in the inverse relation relates B to A. So any relation could be inverted. Now, if that first relation that you started with happened to be a function, right? Then when you take the inverse, you always get a relation, right? But you don't necessarily get another function. This new inverse relation isn't necessarily, again, a function. The theorem, the big theorem, is this one right here, that when is that inverse relation in fact a function, right? When is f, that's when we say f is invertible, right, to another function. The inverse function, the inverse relation is in fact a function, only if f is a bijection, right? That's when that happens. If f is one-to-one and onto, if it's both injective and surjective, right? So now how then do you make such an f that maybe wasn't initially a bijection? How do you turn it into a bijection? Restrict the domain to get it to be injective, and restrict the codomain to get it to be surjective. Then you can write down f inverse and you'll have a nice function for f inverse. So, all right, great. So that's inverse relations and inverse functions. Thank you.